Okay, now that we're recording, for those just joining, we were talking about the final exam, and as I was saying, I need to get grades turned in no later than the 11th, right? Which means I am going to have the exams and the midterm replacement papers are going to be due the 9th. Okay. I will be opening the exam sometime on Saturday, right? And it will just be available until the 9th. I really shouldn't give you guys that long because someone's going to spend that long on it, even though it should be yeah, so this is actually, because the semester's over, this is a really light week calendar wise. And this is just like my weekly recurring stuff. This isn't like all the things that get scheduled normally. Lately I've been spending like 5 or 6 hours a day straight on Zooms. It's awful. But anyway, so the midterm will be due on Wednesday. Our scheduled exam time, according to the registrar, is the 8th, right? So I will have actually, so the exam I'll make available the 6th. So you'll have the 6th, 7th, 8th, and 9th. I will have office hours scheduled the 7th, 8th, and 9th. And the TAs will make sure that they're available as well for that, right? Okay, so let's take a couple quick minutes and just take a look at this. Okay, so I'll come back to question 1 at the end because that's the most difficult one on here. The exams I feel are this practice exam and the real exam were written at the same time. Like I said before, I came up with a list of all the questions. They were approximately randomly sorted, right? Meaning that they were placed into 2 piles randomly, but then I had to do a little bit of switching to get the difficulty between the exams about the same. And then one of them was chosen at random to be the practice, and one was chosen to be the final. Okay. So what you see here is representative of what you see. Of course, you're not going to have these same questions, right? Because I wrote up a bunch of questions all at the same time. But this should give you a clue to the topics, right? The final is cumulative. But it is more heavily weighted towards the stuff after the midterm. Okay. I already said there's not going to be solutions for this posted, right? Because that sort of defeats the right. right? So what do I expect you to do with this practice? I don't expect you to spend hours and hours and hours working through and writing out detailed answers to all of this, right? What I want you guys to do is look at these questions and think about how you would go about solving them. Think about the logic, okay? And then talk to me in office hours Wednesday and the extra office hours that I'm going to have Friday about your logic, right? And that's what I sort of expect. But if we look at the questions, you'll see that we really, most of these are discussion and conceptual questions, right? So these are essays, right? Right? What are the expectations on these essay questions? Okay, so let's look at question 2. So I say consider aluminum copper, right? This was a system we talked about in a little bit of detail, right? And specifically, we talked about the precipitation sequence of GP zones, theta double prime, theta prime, and theta, right? And we remember from the phase diagram that theta is the thermodynamically stable phase, right? GP zones and these other phases are the metastable phases, right? And I ask you to discuss this precipitation sequence, specifically using the molar Gibbs free energy versus concentration diagrams, right? Or the double tangent constructions. Okay. So the first thing you're going to need is to check out the phase diagram, right? There are additional other helpful figures in your notes and your readings, but the phase diagram's the most important, right? That shows the solvus of all these different phases. And then I say, just consider that you're at some fixed copper concentration and discuss the precipitation sequence. And then as you go through it, what are the composition of the precipitate and matrix phases, right? So remember that the GP zones are essentially clusters of copper atoms. So the GP zones are much higher in copper than the other precipitates, right? And then theta double prime is a stoichiometric compound that's lower in copper than the GP zones, right? So if I keep the same amount of copper in the precipitates, what has to happen to my volume fraction as I go up, right? So the copper becomes, the precipitates become leaner in copper, so there has to be more of them, right? And if we look at where the intersections in our common tangent is, it means that our matrix is also getting leaner in copper. Okay, and so I'm expecting a couple paragraphs as you step through all of these with a couple sketches of the Gibbs free energy curves, right? With perhaps some things like the chemical potential, the common tangents in there, and some chemical potential information to talk about what's the driving force, where are things going to move, right? Okay. So the questions you'll see here are much less quantitative, much less computational, more about thinking, right? More
Just because
about,
I'm fucking sleepy, bud.
what's that?
Is he gonna come here right later? I'm really fucking tired.
Okay. Okay, so so the next question, let's look at sintering of a ceramic. This is a figure that's right out of the reading. The question itself, though, is not, right? So we talked about this example, how different conditions can lead to either coarsening or densification, right? And in this case, this is iron oxide sintered in air or hydrochloric acid environment. And clearly we get very different microstructures that have different amounts of different theoretical densities, or different fractions of the theoretical density achieved during the sintering process, right? So what I want you to do is discuss what mechanisms have to be active, right, to produce the microstructures shown in the figure, right? And that's probably a paragraph, a couple paragraphs, right? A paragraph for each mechanism, for each figure, right? Maybe a couple sentences on what mechanisms you need for densification, what you need for coarsening, right? And then I say, what happens if we continue to hold these for a long time, right? If I extended this out for several more hours, what would happen with both of these microstructures? Okay. The next question, I say, consider the growth of a plate-like precipitate from the matrix in the solid phase, right? I ask you to explain why plate-like or needle-like precipitates will form instead, in some cases, instead of spherical precipitates, even though they have a higher interfacial area. Okay. Why do plate-like precipitates lengthen very quickly, right? Compare the expected growth rate against the expected growth rate for planar incoherent interfaces. Right, so that's probably a clue here that I mentioned incoherent interfaces and a comparison. And then why do these plates thicken at a much slower rate? What is the rate limiting step of the growth process? Right? So again, probably a paragraph for each of these prompts, right? With a couple sentences. Okay. Schematic diagrams to show how growth rate and nucleation rate vary with temperature for a diffusive solid state phase transformation that is introduced by an increase in temperature, right? And how is this curve going to be different from phase transformations induced by a decrease in temperature, right? So you got to think about what's the driving force for each, right? And the fact that I say explain how these curves would be different should tell you something, right? If I'm asking you to write things out in a paragraph form, that they should be the same is probably not what I'm looking for, right? Okay. And then the last question is about interfaces, interfaces. So describe the structure and energies of coherent, semi-coherent, and incoherent solid interfaces, right? Pay particular attention to the misfit and strain energy, and use the above description to explain why orientation relationships, such as the Berger's orientation relationship between alpha beta titanium or the Kurgyamov-Sachs orientation relationship in steels develop, right? Right. So 5 of the 6 are very conceptual questions that I'm expecting a well thought out, well formulated essay type response. Okay. Meaning logical sequence, right? Think back to your high school days with 5-paragraph essays, right? Right. I don't want a 5-paragraph essay for each one of these prompts, but I do want a answer, a clearly stated opening sentence with logical sequence of evidential points that support your statement. Okay. Question 1, there is one calculation here, right? Which should be easier than the calculations on the first exam, but are a lot in this case, it's very much in the same vein. I say we have alumina and chromia, and you have the melting points for each. I also say they have complete miscibility in both the solid and liquid state. And I further say, consider that the entropy of melting is the same for both, right? So what that means is that alumina and chromia have the same crystal structure and equal sizes and all that good stuff, so that the entropy change on melting is very similar. And we're also going to assume that both the liquid and solid solutions are ideal, right? So if we take that, I say, if I have a mixture that's exactly 50-50, right, calculate the temperature at which the solid solution begins to melt, right? And then calculate the composition of the first melt that forms, right? So this is doing some phase diagram calculations, similar to stuff that was on the first exam, but again, much easier. And then I say, would you expect the equilibrium freezing temperature to be higher or lower than the equilibrium melting temperature? That should be straightforward, but I want you to explain your reasoning, right? Which means paragraph form, consistent, logical statements, right? I'm really stressing that I want to see things written out clearly, because in an essay type answer, there's, they're a lot harder to grade than calculation-based answers in the first place. So it makes my life a heck of a lot easier. And so there's going to be points based on how you format your answers, right? Which is just the way it is. So for those of you who don't like writing, I'm sorry, but that's life. You don't have to handwrite out everything. If you want, you can make sketches on paper and type up your answers if that's easier for you. That's fine. Okay. And, a word of warning, I still have the same statement, right? here, because of the nature of this exam, right? You probably will be able to get answers if you post on online forums, right? Unlike the first exam, which was just way too hard and no one knew how to solve it for you guys. But, you know, I went a little easy because no one got any help from posting anything. But it definitely won't happen this time. Right? So if I find questions from this exam posted online, remember, between me and the University Committee of Academic Misconduct, we have the power and authority to compel any questions about who posted and who viewed answers. So please don't put me in that situation, and don't put yourself and your colleagues in that situation. Yes, you can definitely use the book and lectures to reference on this exam. General Googling is fine, right? It's open book, open everything, right? When I say open everything, I just use a little bit of common sense, right? Don't put yourself in a situation where it could be considered as misconduct from the university perspective, right? Right. So when I say shared or discussed these questions could very well be construed as Googling this exact question, finding out that someone posted it on a forum and copying down those answers, right? I will revise this statement a little bit more to make it clearer. But yes, the exam will be generally open resources. Okay? So let's talk Martenssite. Okay, so first off,
I have a general question.
yeah, sure, go ahead.
Has Wednesday's lecture been posted?
Wednesday's lecture didn't make it up?
I looked this morning, I couldn't find it, but it might
Okay.
be there.
Yeah, let me sort of, it's supposed to be scheduled. I have a YouTube scheduling thing that's supposed to put them up automatically. And I guess that is somehow broken. Okay. It's supposed to, because I store this, it gets uploaded to a Dropbox, and then YouTube's supposed to automatically post things from that Dropbox. Okay, so immediately after class, I will post Wednesday's lecture and today. I'll do it manually instead of relying on the bot. I wonder why it's not working. Thanks for pointing that out. Okay, so on Friday, we talked about twinning. Well, first off, we talked about civilian versus civilian or diffusionless, or I'm getting all tongue-tied. Talked about military or diffusionless versus civilian or diffusional transformations, right? And we said that the military transformation involved the cooperative or homogeneous movement of many atoms, right? Whereas the diffusional transformation is the uncoordinated movement of atoms by random walk diffusion. And I talked a little bit about deformation twinning to basically set up how you can have a lattice transformation of the lattice, or a transformation that involves a large rotation of the lattice, and that generally there's shear involved, right? Twinning goes from the same crystal structure to the same crystal structure. So in case of FCC, it goes from FCC to FCC. And we have a 60-degree rotation about 111, which gives us essentially a stacking, an error in our stacking sequence. Instead of ABC, ABC, we now go ABC, ACB, ACB in the twinned region. And then that brought us to Martenssite. Okay, so Martenssite is exceptionally important in steels, right? But it's also very important in many ceramic materials. I'm not aware of any polymer Martenssites, although there might be. I just don't know them off the top of my head. But Martenssite is very similar to twinning in the sense that it's a shear transformation. But in this case, we're going from one crystal structure to another. From steel, we're going from austenite to, which is FCC, to body-centered tetragonal Martenssite, which has a higher carbon content than the BCC ferrite, right? And Martenssite is a thermal, meaning it's not thermally activated, right? We don't have to overcome a activation barrier for it to occur. Once the Gibbs free energy is there, it transforms. So we have a well-defined Martenssite start temperature, and we will, as we keep lowering the temperature, we will create more and more Martenssite until we get to Martenssite finish, right? The TTT curve also shows us that we have to quench fairly quickly, right? Because if we cool slowly, we're going to nucleate pearlite. Or if we go a little faster, we're going to enter into the Bainitic region. Okay. So Martenssite here, I said it's largely athermal. It occurs when you do not have a change in composition. So that means for it to happen, we have a situation that's quite different than for diffusional phase transformations. In a diffusional phase transformation, if we're at a composition out here, right? Say we're at a higher concentration than C0 on this diagram, right? As long as we're between these two common tangent points, we can lower the overall free energy of our system by decomposing into alpha at this composition and gamma at this composition. Okay? But that involves nucleation and growth and diffusion, right? We cannot transform directly from gamma to alpha at this composition by a Martensitic reaction because the free energy of alpha is higher, right? So without long-range diffusion, we can't lower our free energy. The transformation will only raise it. But once we're past this intersection point, we can locally lower our free energy by going directly from gamma to alpha at the same composition, right? So if we're to the left of this intersection point, we don't have an activation barrier that we have to overcome. We don't have an energy penalty that we have to pay by nucleation. Okay? And so What that means is that we're going to nucleate and grow outside of what we of everything that we talked about with respect to the common tangent, right? It's completely a local driving force, right? The transformation to Martensite does reduce the overall global free energy, but we could reduce the global free energy diffusionally over here, right? But the local free energy isn't, right? It doesn't, is increased by nucleation, but globally we decrease. Here we locally reduce, right? And if we locally reduce everywhere, we also can globally reduce, but we have to be at a much lower temperature in order for, at our composition, this austenite free energy curve to be high enough and our ferrite free energy curve to get low enough, right? So that we have a sizable delta G for the transformation to occur. Okay, so if we look at what are the enthalpy change and our Gibbs free energy change on formation of martensite, we can see lots of these are metallic systems that undergo martensitic changes. And take a look at the Gibbs free energy change for iron carbon relative to everything else. Okay, so compared to other systems, the driving force for martensite in steels is huge. It's astronomical, right? You know, it's in some cases 2 orders of magnitude higher than other systems, right? This is why in carbon steels, if you quench, and even in some systems, if you air cool, you're going to get martensite. Just because this driving force is huge, right? Notice it doesn't list an undercooling, right? Because a lot of systems, the driving force is so high that there is no concept of an undercooling for martensite. It's just so astronomically small we can't measure it. Okay. So for twinning, right, we said that we had two undistorted planes, right? The first was the invariant plane or the twinning plane, and then we had the plane of shear, right? In martensite, we have something very similar. We have the habit plane, which is also an undistorted plane, okay? But because we have a phase transformation, we actually have to have other strains besides the shear. We actually, in martensite, we have a volume change as well, because we're going from one crystal structure to the other, right? So there's a volumetric change. Sorry, my desk chair is just suddenly very uncomfortable. We have a volumetric component to the change as well, instead of just the shear component. But we need, for crystallographically, for this all to work out, we still need our planes, our invariant planes. So that makes the crystallography of martensite more complex than the crystallography of twinning. Okay. So if we look here at different systems, we can see that the shear component of the transformation is quite large. Okay, so if we look at iron, carbon, steel, right? Remember FCC to BCT, right? This is the habit plane and the shear direction, but take a look at the component, the amount of shear strain associated with Martensite formation. 20% strain, right? 20% shear strain. That's huge, right? What is the elastic limit, right? What is how much shear strain do we accommodate elastically, right? What's your offset that you use when doing a stress strain analysis? 0.2%, right? So 2 orders of magnitude higher. So this should tell you something about this transformation. This Martensitic transformation is exceptionally violent. What happens if I'm here, I have a 20% shear? What happens in these neighboring grains? How does this get accommodated in a polycrystal? What has to happen? I need plastic deformation out here, right? To occur, right? I somehow need to maintain the continuity of my polycrystal without breaking, right? So some of that can be done if I have things out here that have the opposite shear, right? I can do some accommodation that way, but generally there also has to be plastic deformation that occurs. And what's the volumetric component? In this case, the change in our lattice parameters when I go from FCC to BCT is close to 10%. So my overall strain in my system from Martensite becomes very large. And yes, it does actually form a chain reaction. Right? I'll talk about that in just a bit. Okay? So we have this shape deformation in Martensite, this large shear. So we end up with shapes that look a lot like deformation twins. Okay? These lenticular shapes come about because this is what minimizes the elastic strain energy. In a graduate class or in a mechanical behavior class, we talk a lot about that strain energy minimization, but it's not super important for the purposes of this class. But Martensite near the surface actually causes surface relief, right, due to this shear. Right? And so if we have a unconstrained transformation, we get a big kink. If in a polycrystal where we have constraints, we get these lenticular shapes instead of big plates or slabs, because this is going to help maintain that the shape and minimize the elastic distortion and the amount of plastic strain that has to be accommodated by the neighbors. Okay, so Martensite in all systems generally will form orientation relationships. The orientation relationships in carbon steel is generally quoted as the Kurdyumov-Sachs, which has the close packed directions parallel with each other, right? In iron nickel, we see a relationship that's called the Nishiyama-Wasserman And then we have a whole family of orientation relationships called Grenier-Triano, which are intermediate to Kurdyumov-Sachs. Now, the thing about Martenssite is in steels, the transformation pathway is dependent on the amount of carbon that you have. And the volumetric strain that you have is dependent on your carbon concentration. So we never actually observe any of these ideal orientation relationships. It's always somewhere in between because the carbon content is not always spot on for these to occur. And we'll talk about that on Wednesday. To wrap this up today, I want to talk about how do we actually go from one lattice to another, okay? So if we start with FCC, how do we end up as body-centered tetragonal? Well, Bain back in 1924 said if I stick two FCC unit cells together, I have this triangular bit here that's BCT. I have another way of describing the FCC unit cell is I can create an equivalent lattice of body-centered tetragonal elements that have and it's completely equivalent with respect to the lattice positions. And so Bain said, well, this is obviously way too distorted. This is much too tetragonal. But what I could do is squish it down a little bit and make it more square, right? And this is what he called the Bain strain. This is what is now called the Bain strain, okay? And so by expanding or contracting these crystallographic axes, we get what is known as the Bain distortions. However, this theory, as we went on, realized is not true, okay? Because there is no invariant plane, right? So in order to get an invariant plane, we need something beyond this Bain distortion, right? We don't have the two planes, the two shear planes, where we have perfect atomic congruence between the FCC and the BCT. So in order to get that relationship, we need something more, right? And that's a series of steps that are called the phenomenological theory of Martenssite. And we'll talk about those on Wednesday. Okay? So Wednesday we'll talk more about Martenssite. I hope to begin talking about diffusion in polymers and glasses and vitrification. Realistically, though, I may have to record those as sort of some extra lectures for those who are interested. But I'm not going to leave you hanging, right? For those polymer people in the group and glass people, I'm not going to leave you hanging. I promise. Right. So have a good one. And there were a couple people who had some questions after class. So you guys can hang around, but I'm going to stop recording.